immediately up to vehicle. You can have a pony, which is also be a mode of transport, but it's animate. These are inanimate things. You'd have to go right further up the hierarchy and travel back again. So it's a longer path, more distance. That's just one of the 5 measures. Latent semantic analysis is the interesting thing about that is that claims have been made about its connection to human language. This is interesting. The similarity judgments produced by latent semantic analysis, it's shown to correspond to, in some ways, to human similarity judgments. For example, after training on about 2,000 pages of English text, it scored as well as the average test taker on the synonym parts of part of a test, that is the English as a foreign language text. Even more interesting, after training on an introductory psychology textbook, it achieved a passing score on a multiple choice exam. But of course, it's not without its detractors. It's merely a statistical technique to measure how similar the context of use are for 2 words, and just in terms of the words that are around it. But it does give some surprisingly interesting results. The Google-based similarity score is derived from the Google distance, and it can be, this is extracting data from the internet using any search engine. Intuitively, the Google distance, normalized Google distance, is an estimate of the symmetric conditional probability of co-occurrence of the words X and Y, and it's transformed into a similarity measure in a straightforward way. So, what can we do with these? Now, LSA and the Google-based NSS provide straightforward measures of similarity. That's what they do. But for WordNet, as I explained, there's several revised, and we use a combination of those. Here we have, for this set of words, London, Moscow, Paris, North, South, East, West, Germany, Poland, Russia. This is the semantic similarity matrix derived from WordNet. What we did here is we used only the senses relative to the geography of Europe. So one of those Paris words, and then North, South, East, West had several senses that were left out. So we restricted the senses that we took and took these similarity measures between them. So that's the kind of thing we can do with the language data. I showed you the WordNet one, show you one for LSA and for Google-based NSS, completely similar. So what are we interested in doing? We want to find structural models for the brain and language data. What we do, first step, is to analyze the brain data using a statistical model that predicts to which class of brain data sample belongs. I used a discriminant model, courtesy of Marcus over there, who you're going to hear from more later. So taking these 10 words, they gave us 640 data samples classified into 10 classes. So more generally, T brain data samples, S1 to S10, are classified into the N classes, W1 to Wn, and roughly speaking, those classes represent prototypes that we compare the actual data samples to. If a test sample Si is classified as W1 and W, what's that, J, have a minimal similarity difference compared to the other possible classifications. So here we have 640 brain data samples classified, and we look at the confusion matrix, standard confusion matrix from the classification, and from that we get the estimates of the conditional probability densities. So now we have, for the brain data, a similarity matrix akin to the ones we have for the language data. It's useful to see what's going on in that similarity matrix. Here's a hierarchical cluster tree computed from that matrix we've just seen. So that was a classification, and this is how the classification grouped the words, really quite pleasantly, with the east-west or south together, the cities together, the countries of Germany just a little confused. Now, every single trial classification produces its own conditional probability density estimates, and so it gives rise to its own similarity tree. Here we have one that's not quite so well behaved in terms of cities and country. Back to semantics for a moment. We had the word net similarity matrix. Here's, to get a sense of what's going on there, here's a similarity tree, a hierarchical cluster tree, which is very neat. The word net does a great job. It's very well organized. It was manually crafted. This is for the latent semantic analysis. Here's a cluster tree from its similarity matrix. It just has Moscow grouping itself with those three countries. And here is the Google-based normalized similarity scores, which is very much less well behaved. So some of those similarity trees, and on some classification runs, you get some fairly intriguing congruence, it seems, between the brain and semantic data. But where exactly does that congruence lie? And can we devise a quantitative measure of the nature and strength of that congruence? Well, yes, we can, thanks to the work Pat has done. So, having computed the conditional probability density estimates, we can, for each word, define a returning relation R prime, such that it holds if and only if it's between W and W1 and W2, and this is for the word W. This relation holds only if W's one's similarity with W is smaller than W2's similarity with W. So R prime is actually an ordinal relation of similarity differences. It's a partial order that is irreflexive, asymmetric, and transitive. And we do exactly the same for the semantic models. We get partial orders. And what we're doing here is actually have two structures. That's the article I kept on finding myself going back to with that. That we have a relational structure, R prime, for the brain data, with all its partial orders, and a similar one for the language data. In fact, we have three of these, one for each of the models. And what we're going to do to compare the brain data and the language data is compare the partial orders of each structure. First of all, just use Spearman's rank correlation coefficient, which we interpret in the usual way to determine if we have a statistically significant correlation or not. And for those instances in which the brain and language partial orders are significantly correlated, we find the partial order that is invariant with respect to the brain and language data. And here are two examples, both with respect to Paris. So these organize in fairly nice ways, the directions at the top there, then the countries, then the cities. The one on the right, the south, its similarity differences, its similarity, semantic similarities, there was not an invariance between the brain and the language data, so that lies outside of this invariant partial order. So these are just two. Pointed out, every single classification run will produce its own partial order, its own probability density estimates. So what we did is we performed a series of computations, let's just say 30, that's what I'm going to show you. Computed 30 single trial classifications of the data, in this case 640 data samples, using random resampling with replacement. Each classification, we find the partial orders that are significantly correlated, brain and language, and then for each of those, as I explained, we find the partial order invariant with respect to both. We do that for WordNet, latent semantic analysis, and Google-based NSS. And these are the results we get for 4 subjects. So S18, S24, S10, and S25. The one on the left, S18, out of the 300 invariant partial orders, significant invariant partial orders that could have been found, when WordNet was used as the language model, we found about 260. For LSA, about 160, and for NSS, just over 100. And for the other test participants, we found a similar staggered result. WordNet gave the largest number of significant invariant partial disorders, except for the subject number 25 that I've shown here, which had this little bump up with NSS. Interesting, that subject only got 60% of the geography questions correct. The one on the far left got 91%. So, I don't know if it's got anything to do with it. So, the original conclusion I drew from these results is that the brain data reveal evidence of context-sensitive processing, because the number of statistically significant structural similarities found between the brain and language data is greatest when the language model is strongly restricted to be contextually relevant, that is, to the geography of Europe. For a language model that is less subject to contextual restrictions, such as LSA, the brain and language data exhibit fewer statistical significant structural similarities. And for a language model that is subject to low contextual restrictions, there are even fewer statistically significant structural similarities. Lately, I've been asking, though, do these results instead tell us something about these semantic models? Is it perhaps that WordNet is a better model of some aspect of language processing than LSA? Is it a better model of how the lexicon is organized in the mind, a better model of semantic knowledge? So it's not altogether clear what to conclude, but it's certainly interesting. Those are the results I wanted to present today. Now, most people have been ending their talk by saying thank you to Pat and happy birthday, but I'm going to take another tack, because as we know, Pat likes nothing better than a good argument. So I'm going to end on another question, which is picking up a conversation Pat and I have been having for a few years, and we have not yet resolved it, as to which are the best experiments to follow up with here to tease out what's happening. And I hope we pick that conversation up again and come up with a good answer.